this is the power of multi-tenanted architectures. Look, if you deploy your services on Dynamo on demand and S3 and you hit 1 million requests per second, like chances are that it will work. But if you had like concocted your own EC2 based framework and you are confronted with an unanticipated spike, chances are you're screwed. So these multi-tenanted serverless services, they just are way more capable of handling the scale. Why? Because
Hi, welcome back to another episode of Real-World Serverless, a podcast where I speak to real-world practitioners and get their stories from the field. And today we are joined by the Khawaja Shams again from Momento. Hey, man, welcome back.
hey, Jan, always good to see you.
Yeah, we spoke a little while back about the Memento, and I've been a big fan of what you guys are working on. And recently, I saw a post on LinkedIn from one of your engineers talking about how one of your customers suddenly just decided to do, I would say, like 1 million requests per second, and it has some like small impact. I think you were talking about a nanosecond difference in terms of your architecture response time. And something came out interesting from that conversation, which was about cellular architecture and something that I know you guys have been doing at AWS previously. So,
Mhm.
yeah, maybe before we get into it, tell us a little bit more about Memento and yourself again, and how you got from AWS to Memento.
Yeah, happy to. My name is Khawaja. I started my career building cameras on board the Mars rovers. Um, I'm impatient, so I moved on to building software. Software is much more instant gratification than hardware. Built the image processing pipeline for the Mars rovers. Impatient again because I didn't want to wait for servers. So in the around 2008, 2009 timeframe, I moved my entire pipeline onto AWS, um, using a lot of the original serverless services, S3, SQS, to really power those image processing spikes. Um, I joined Amazon, ran the DynamoDB team, and then worked at AWS Elemental to run product and engineering for the media services. Um, and today I'm a co-founder at Momento. We take a lot of the lessons that we've learned building high performance, mission critical, high scale applications, and make it easy for our customers to do all that without having to worry about the low level infrastructure minutia, specifically as it pertains to caching and messaging.
Yeah, I really love the stuff you guys have done around the topics. The topics it just makes the building real time communication systems so much easier in terms of building some kind of like a push model for your website background processes to tell the front end that something's done, or something more interesting like real time chat or games where you need to communicate in real time updates from one place to another. Like topics just works really well for those use cases, and it's so simple to use as well. I know AppSync has released a new event API to try to make it a little
Mhm.
bit more accessible for folks who want to have that, nice managed WebSocket, I guess messaging without having to use GraphQL. But I think compared to Memento topics, it's still lacking some of that fine-grained access control for one. But also, I think just in terms of like, how easy to use, yeah, you guys have done a really good job around the topics.
Thank you. I think developer experience is key for us, and that includes how quickly people get started, but also how little distractions they have to deal with when things get big and spiky. Um, the our main value prop is just to get customers going and keep going when as their events become successful. And we constantly look for sources that distract customers. And WebSockets, like fighting with WebSockets, tends to be a pretty frequent occurrence for anybody that is trying to build real-time notifications to end applications. And we saw that as a great opportunity for us to add value to the world by kind of simplifying how quickly people can add messaging to their front-end applications.
Yeah, talking about like the distractions, thinking about the uptime and the redundancy and all of that is also a big concern as well, especially as you start to build things for millions of concurrent users, really high throughput systems, and that's one of the things that you guys are really good at in terms of just that scaling and resilient architectures. And a big part of that is something I want to talk about today, which is around cellular architecture, something that I've been reading more and more about, and something that I guess folks like Mark Brooker has talked about quite a lot in terms of multi-tenancy and AWS. And I know that you were involved with a lot of those discussions while you were at AWS. And yeah, so maybe tell us a little bit about that the incident that happened at Momento, and how it kind of you guys are using cellular architectures to kind of I guess limit the blast radius of what that one noisy customer was doing.
Yeah, I mean, I think let's go backwards in time and talk about why Amazon went all in on cellular architectures. When AWS initially came out, the Virginia region was, quite popular. I mean, it was the first region, and it was the default on the console. So a lot of the customers ended up just defaulting to deploying their services in Virginia. James Hamilton always talks about the power of defaults, and I'm always surprised by how much people just pick whatever is the default. And what happened over time was that the Virginia region kept getting bigger and bigger. And you'd basically learn about all of the scaling limits. If you were a service provider inside of AWS, all of your limits of the architecture, of your software, everything would get exposed first inside of Virginia region because it was the biggest. And if you look at some of the biggest outages that have happened in AWS, most of them are at least historically, most of them were in the Virginia region, and a lot of them were just due to the scale. And you can do all kinds of staging and throttle your deployments and so forth. But by the time things get to Virginia, they had never been tested at that scale. And for AWS, one of the Mark Brooker's principles is, do constant work. And if you look at it, the region with the highest density of customers had it was most unlike every other region. So when that region messes up, you mess up a lot more people, but that's also the least tested. So the brilliant folks at AWS came up with this notion of, well, we can cellularize the regions and the services within the region. All that means is you divide up the region into small cells. And this way, your cells start to look a lot more similar to each other. IAB might have, or Virginia might have lots and lots of cells that are closer to the size of the second biggest region, or and so forth. But it also gives more engineering constraints for the people who are designing the architecture as well. So around circa 2015, right after AWS purchased Elemental and we were launching a bunch of media services, the edict inside of AWS was to start shipping all the services to be built with cellular architecture from the ground up. So I got to experience building those services, and it's kind of mind blowing how much just thinking about reducing the blast radius goes in terms of increasing the overall availability and improving the design of your service.
Yeah, I remember back in the day, it wasn't just the US East 1 itself, but the US East 1A. Like specific AZs was so much bigger than others, again, because it's a default. And someone, I think it was Corey Quinn, was joking at one point that if you want to run the chaos experiments, just deploy your workload to US East 1, because essentially it's going to be doing that, because all the failure is going to happen over there compared to the other regions. And I remember, what was it, about 7, 8 years ago, they started to shuffle around different AZ so that your US East 1 is not mine US East 1. So that way they were able to, I guess, again, just moving customers around to different AZ so that they're not all concentrated on the US East 1A, which is, again, the default AZ for everybody. So in that case, like a question that comes up a lot is, how does cellular architectures differ from something like microservices? I guess from what you described, cellular architecture is basically taking your one maybe microservice, but deploying different copies of it, and then you put different customers into each of those cells, so that when one customer is doing something crazy, they may be a noisy neighbor, but they're going to be a noisy neighbor for 10 other customers, as opposed to all the other customers in the same region. Is that the idea that you're dividing your customer into different sort of groupings as opposed to dividing your application into different services, as is the case with microservices?
I think that's one way to think about it. I think you hit the nail on the head with microservices. Usually, when you think of microservices, there's some heterogeneity, right? There's different variety of microservices. Cellularization is to take the same service and then break it down into lots and lots of cells. And the core value prop here is to just reduce the blast radius of what happens when a cell goes down. Cells can go down for lots and lots of reasons. It could be a bad customer or a customer having a bad day. It could be because you have a bad deployment. And all of this, again, comes back to reduce the blast radius and then giving the team engineering constraints that this is how big you expect your cells to get to. Um, the so that's why people cellularize, and the idea here is you can cellularize and put customers in specific cells, and that's a good idea for many reasons. It helps you do better capacity planning and so forth. But if you really go all in on cellular architecture, you can get to a stage where you can put your largest customers within their own dedicated cells as well. And if you do this from the ground up, this actually helps you in many ways. And this is one difference in the way Momento does cellular architecture than a typical AWS team does cellular architecture. AWS teams will have lots and lots of customers within a given cell, and their job is to improve the utilization of each one of those cells. The way Momento does this is for our largest customers, we give them their own private cell, but both our cells and AWS's cells are multi-tenanted. So, and multi-tenancy helps you improve utilization and so forth. In our case, our customers benefit from the increased utilization by leveraging multi-tenancy within their own organization, and we can make trade-offs that are very customer specific in terms of how hot to run a particular cell. So having this cellular architecture allows you to have degrees of freedom across different customers as well if you really, really go all in. And fundamentally, at the bottom of every cellular architecture is how do you quickly deploy cells as as the customers demand, and having a really good infrastructure at code stack really allows you to be nimble and to deploy a cell for every customer without having to spend engineer weeks building out a cell for each region or whatever it may be.
Right. And that's one of the multi-tenancy strategies that I think AWS has often talked about in terms of having essentially, tenants. Every tenant gets its own copy of the same application, and one of the trade-off there has always been, okay, now you have to put a lot more work into automation and make sure that when you push out a code update, it's going to get deployed to all the customers quickly. And okay, what do you do when this one of the customers or one of the tenants, one of the cells fails to update? What do you do at that point? What are some of the sort of, I guess, real world problems you guys have run into with this kind of things, like deployment taking a very long time because there's so many different cells? And what do you do when maybe there's some problems that are happening? You don't know if it's to do with the new code change. Do you just keep going? Do you roll back? What are some of the kind of real world problems you've run into?
Yeah, I think uh, Amazon ran into this problem as well. We run at it into a much more modest scale. When Amazon in the early days just had a handful of regions, and the trade-offs that we made on how we design deployments, how do we do staging and so forth, the trade-offs that work when you have five regions don't work when you have 5 dozen regions. And we're running into some of those problems now because, if you're putting a day of baking across each of your stage, now either your stages get very, very wide, or it's taking you weeks to deploy software, to do forward deployment. So cellularization is, it gives you more cells, but it actually slows down your deployments a lot. And that's a big problem. And the challenge here is that if you overcorrect and say, okay, now I'll just deploy to 50 cells at a time, well, you defeated the purpose of reducing blast radius as well, right? So then you're back to the same problem. So you got to be very, very mindful about your deployment strategy with cellular architecture. The other AWS tenant that we're starting to question a little bit in terms of, as we evolve our old cellular stance, AWS puts every cell in its own account. That's the internal best practice. And that's a really good practice. But, if I have to log in or if I have to track my resources across lots and lots of accounts, that gets very challenging as you start hitting into, nearing 100 cells. Like that becomes like now you have to find the account, you have to make sure you're in the right account. Any diagnostics that you're doing, capacity management across the fleets, that becomes much, much more challenging. So the new feature where I can log into multiple accounts from my browser in the console, that's very useful to us. But even then, it's really difficult to deal with the number of accounts. So we're now starting to question, do we really want each cell in its own AWS account, or do we want to get better at deploying units of changes for our customers, but stick within, have fewer AWS accounts along the way?
Yeah, I heard that as well about AWS internal best practices in terms of security team only trust the account boundary as the only kind of boundary that they fully trust. Is that the only reason why everything have to be deployed to their own accounts?
It comes back to blast radius. So imagine if the account gets hijacked, or if the account gets deleted for any reason. Um, you or somebody does a bad deployment where they reset the password of the account, or they delete all Dynamo tables in the account, right? Like anything, and hopefully you have more than one, because blast radius with STDs is pretty bad, like single table design. But anyways, the point being that it's a really nice isolation boundary for blast radius reduction, and one bad deployment doesn't mess up anything else. And now the account boundary serves as a namespace. So in each one of my cells, I can have a Dynamo table called control plane metadata or whatever, and that's totally fine. Whereas if you're keeping each cell, multiple cells in the same account boundary, then you got to have their names associated with it. And then your access control becomes a little trickier because now you got to create IAM policies for each deployment that, so that particular account has uh, only access to its resources and so forth. So things get a little more challenging to enforce and to reduce the blast radius if everybody shares the same account. That's where the trade-off becomes even more exciting and interesting.
Okay. And was it true that even when you guys were doing multi-region applications, every single region have to be in a different account? So it's not just multi-region, but it's also multi-region and multi-account.
Yeah, each region should have multiple cells, and each cell should be its own account. And that's true in Momento today as well. Like we have lots and lots of AWS accounts in lots and lots of regions. Like another real world thing that we run into, limits. We make a brand new account, and then like today, I'm actually really proud of our infrastructure as code capabilities. Like we can pull up cells in a matter of an hour, but it takes a little bit longer to get it productionized. Why? Because we're waiting for tickets to get our limits increased on a brand new account.
Oh yeah, remember those days? Every time you open a new account, there's a bunch of limits you have to raise around EC2 and the VPCs and all this other stuff. Another thing I always wondered about cellular architecture is that, with AWS, it's already quite difficult to think about SLAs and availability when a given service is never really quite down per se because it's always available in some other region. Um,
Mhm.
but when you have multiple cells within the same region, how do you start to then reason about SLAs and your uptime, especially when there are monetary, refunds and credits involved when it comes to SLAs, and when you have violated your SLA? Do you have to do that at a cellular level or at a customer level, or is that something that you only measure at this kind of service level or region level?
We have to measure SLAs at the customer level. And I learned this the hard way. I used to do this very, very wrong. I remember I showed up to the yearly planning for Dynamo, and we very proudly said, "Hey, for the last year, we've had 100%. Like we met our fleet-wide SLAs at 100%." And the EBS team was in the room, and I think it was David Richardson who raised his hand and said, "Bullshit. That's not true. We know." When like we've had an impact because of you guys. And it was really eye-opening for me because he was absolutely right. And what was happening in the Dynamo team was fleet-wide error rates were fine. They were always below the 99.99% SLA that we took internally. But what happens is from a customer perspective, if a single partition is down, that customer is meaningfully impacted, even though it's one of the hundreds of thousands of partitions in the region, right? So while as Dynamo team, we could come in and say, yeah, like we won, like the fleet-wide error rates are super low. That customer is clearly not being represented by the internal SLAs that my team had. So then we very quickly moved towards measuring SLAs on a per customer and per table basis. And that's a lesson that we've carried on in Momento. So you want to measure your availability and your error rates on a per customer basis, and you need to give them monetary compensation for the SLAs that you agree upon based on their experience as opposed to your fleet-wide experience.
Okay, so in that case, now that we've kind of laid the land for around the cellular architectures, want to talk about that particular incident you guys had
Yeah.
with that crazy customer?
I wouldn't call them crazy. They had
Crazy
a
scale.
spike. Yeah, crazy scale. I mean, this is the power of multi-tenanted architectures. Look, if you deploy your services on Dynamo on demand and S3 and you hit 1 million requests per second, like chances are that it will work. But if you had like concocted your own EC2 based framework and you are confronted with an unanticipated spike, chances are you're screwed. So these multi-tenanted serverless services, they just are way more capable of handling the scale. Why? Because any spike you can do, we've probably seen it, right? So if you show up today and start running 10 million TPS on a Dynamo table, you wouldn't be the first. And the system as a whole has been architected and tested repeatedly for it. So that's the key value prop of these large scale multi-tenanted systems. In our case, we had a customer that had a good day. They're a gaming company. They had a great day, and their traffic went, I think, from 10,000 TPS to over 1 million TPS. And the funny part was Pratik, who saw this, he was on call and he just woke up and he realized that, okay, like, but when he woke up in the morning, that overnight this big spike had happened and we didn't even notice it. And this was nice. I mean, it's a big change for a company like ours because anytime a customer would have spikes, we would love to in the past know when they're anticipating those spikes, and we would work hard. We'll make sure like everything is there and ready, and we have run our load tests and so forth. And now it's getting to a point where it's like, oh, cool, you did a couple of million TPS and we absorbed it and we didn't even notice. Like there were times when like right when you launched the service, like we would have alarms go off if usage went above a certain threshold, just so we can keep an eye, even if something wasn't wrong, just so we can, because if a customer is spiking up that high, maybe it's a really crucial time for them and we don't want to let them down. But this was a really welcome change. Now, the the paranoid operator in all of us isn't going to let that go either, right? Like, okay, you bumped up a over 1 million TPS. How did the fleet do? What were the corner cases that we ran into? And we observed that, hey, we did have a 200 microsecond bump at our P99.9 latencies. So then we started digging into, well, why? It's not like we were capacity constrained, but why is it that these latencies went up? And that started the conversation around just diving into the metrics and asking the five whys until you get to the root cause of where your performance issues are coming from, even if there isn't a major observable customer impact, because that's how you continuously improve your service.
Right. And in that case, with your architecture, I mean, with one cell, how far does that cell go in terms of? I mean, with microservices, you have every service has got its own deployment, its own cluster, and all of that, its own databases. But then there's still that communication between different services. So if you are taking your one of your services and you're deploying different cells of that service, you still have to talk to maybe other services. There's still those interdependencies between services. How do you then, so I guess, orchestrate that? Do cells have to talk to specific cells on the other side, or is that just all down to the routing, or based on a customer ID that the other service will have its own cellular network of different clusters, and they would
Mhm.
route based on a customer ID or something to the correct place?
Yeah, so today, Momento cells are self-contained. So, for reference, you could think of us as a caching fleet. We have it's a two-tier architecture. There's a routing fleet and there's a storage fleet. And the cells don't, there's no cross-cell communication today. When we build cross-region replication, things like that, we might have it. But for now, a cell is fully contained and can only talk to resources within the cell itself. So requests come in, the routing fleet terminates the request and then sends it to the storage node based on after authenticating the customer, looking up the metadata of the cache that they have access to, authorizing the request, and then sending it that particular direction. Um, but as you start thinking about scaling your cell, we're a horizontal caching, horizontal scaling company. Vertical scale makes a big difference in how far up you can scale the horizontal aspects of it. And we gave our engineers a very specific engineering requirement, which is be able to deal with um, 100 routers in your cell and be able to deal with at least 100 partitions, and each partition will have some replicas. So that's how we kind of started. And today, and just at 16 cores, like our routing fleet does like a couple of 100,000 plus QPS. So 100 nodes gets you 20 million QPS, assuming perfect balance. So that on the order of 20 million TPS on a single cell is the engineering constraint that we live with. Our storage nodes do the same. It's 200,000. And that's a number that we have come a long way from. When we are running in the Java world, the number was 20K per node. And we were using 4XLs for it. Now we're, working our way down to 2XLs and doing hundreds of thousands of TPS. But the idea is very simple. Like now we put engineering constraints um, on what a size a cell could be from a physical nodes perspective, and then we work really hard to drive what each node can do so that we can handle bigger horizontal scale. If a customer shows up and wants to do more than 20 million TPS, chances are we're going to tell them to uh, to split between multiple cells.
Right, gotcha. Okay, and when you said the QPS, that's queries per second, so basically
Yep.
TPS for the routing layer. Okay, so in that case, I forgot which service I was using. I think it was the time stream service, which you
Mhm.
have to actually, as a user of the SDK, you have to choose which cell you want to connect to. And is that what you meant when you say when a customer wants to do 20 million TPX, they have to make a conscious decision which request goes to which cell? Is that the what you meant?
Yeah, I mean, we haven't had a customer show up yet above 20 million QPS. So if somebody does show up or TPS, like if somebody does show up and wants to do 100 million, chances are we're gonna, have them split across. In our world, the cellular information is baked into the request token as well. So the JWT that we vend you has all of that information. So each cell has its own, again, it's fully isolated, fully contained. So your tokens today don't work across the cells either. So you'll have different tokens for each cell, and that's how you make the decision between which cell to go to.
Okay, gotcha. I mean, so well, bear in mind that all these extra complexities you have when it comes to cellular architecture, where would you say are the kind of the I guess the threshold when someone should consider, okay, when we're building a service, we should build it with cellular architectures versus just try to squeeze everyone into one cluster essentially.
I think we got lucky because we started cellularization in the very early days. There's a life principle that I live by, which is you'll always be busier tomorrow. So the temptation is always to say, let me build this thing out, and then I will get back to cellularization later. So if you have multiple customers and if you are going to deploy in multiple regions, it's worthwhile to, even if you model your initial service as a single cell, there's just good habits that get built into your setup. Having the right infrastructure as code, having the right deployment setup, all of that is incredibly helpful to invest in and easier to invest in at first, and that keeps you focused. That's when you go from that single cell to then the second cell. This is where you then start to make um, changes in your deployments, and you're having your staging environments and things like that as well. And in our case, our dev environments is a cell, so every developer at Momento has access to their own cell that they can whip up just by running their CDK scripts. um, and our staging environment, it's a cell. Our load testing environment, it's a cell. Every region has multiple cells, and that has been an incredible productivity boost for us. Whereas in Dynamo, at least when I was on the Dynamo team, we used to have dedicated regions or deployments, and like developers would check out a region and say, "Hey, everybody, I'm going to go work on this cluster. Nobody else touch it." Whereas our investment in cellularization at Momento have paid off, where every developer can just spin up their own cell at their whim.
Yeah, it's funny because what you talk about is basically what I've been preaching and teaching my students about ephemeral environments.
Hmm.
I don't call them cells, but essentially it's just a copy of your entire application that you can bring up in its own stack, and you can have multiple stacks. And so you will have your main dev, test, staging, production environment in their own account. But say in your dev account, you have just bring up a copy of your application, your service for development for individual developers or for feature or for a CI/CD pipeline run, so that at the start of the pipeline you create a new temporary environment, you run all of your tests against that, and when you're done, you tear it down so that you don't have to worry about polluting your main dev environment with test data, and every developer and every feature has got its own environment or cell in this case. So it feels like more or less the same idea, so that if you got your infrastructure as code right, so that you can make sure that you've always got something like a stage name or environment name or cell name as part of the resource name, so that you can always tell that, okay, even though I got multiple copies of the same DB table, they belong to different cells, so that I can, and then within that I can still do multi-tenancy, so that I can follow the same practices around using the tenant ID as the hash key, and doing a tenant level IAM permissions and things like that, so that I can still use those techniques, but then I can create different copies of my application as different cells, so that when I need to, I can then bring all of it together, create different cells, and scale out in terms of cells, as opposed to just bigger and bigger DB tables and cognitive user pools and so on. That's actually a really interesting way to think about it. I haven't really quite connected the two together, even though now that you mentioned it, it's basically the same thing.
It's absolutely the same thing. I'll just share a different perspective. You call them ephemeral environments. I think that is one attribute of those environments. The other attribute is they're isolated environments, right? They're isolation units, and a cell is an isolation unit. And sure, the ephemerality is nice because it's temporary, but you could also have the same, like if your students had an ephemeral environment, but they wanted to keep it forever, that would be a cell,
Right. Yeah, exactly.
right?
Because the
Because of
dev
the
environment
isolation.
essentially it's a permanent environment, but it's still
Exactly.
using the same technology and the technique for building ephemeral environment.
That's right. And
Okay.
if you build this ephemeral environment, then your load testing becomes easier. Your ability to reproduce issues becomes easier. Your abilities to develop becomes easier. It's a really worthwhile thing. And I keep getting back to this. Like the reason why you do cellularization is to reduce blast radius. And the way you do cellularization well is you invest in infrastructure as code.
Yeah, and again with the like serverless, the pay-per-use pricing model as well, and then one of the benefits, and I think one of the reasons why kind of this whole practice became more prevalent with serverless, at least for me, is that well, it doesn't matter whether you've got 10 copies of the same application or one copy. You only pay for what you use. So if
Right.
you're doing 100 requests, well, that's 100 requests across one environment or across 10 environments. It doesn't matter. It's the same cost. There's no cost for extra uptime for different redundant copies of the same application.
Absolutely. The consumption-based environments work really, really well for us. In fact, one of the best ways, you know, a lot of customers end up saving money when they move over to us because of the fact that they don't have to have the fully provisioned resources in both of their staging and in their dev environments. They can just, only pay for those resources when they're actually running the test.
Okay, yeah, that's great. This has yeah, this has been whew, my eye-opening moment for me in terms of thinking about the cellular architecture. I guess in that case, you guys been doing some pretty heavy loads already. What has been some of the lessons you've learned so far? Besides, okay, you should always start with cellular architecture so that at least you are ready for it when you need to, start to bring out the second cell and the third cell and so on.
Yeah, I think make the investments early. And the best way to make investment towards cellular architecture is to invest in your infrastructure as code pipeline, and your observability pipeline, because the more cells you have, the more important the observability practice becomes, and it pays off later. The other part, as a our real world experience, a lot of it has to do with performance tuning and scaling up the environment. And we've learned a lot about how to save money and how to be more efficient. And sometimes paying attention to that actually improves your performance and the scale that you can handle. And there's all kinds of things that we're learning around different workflows are better with different EC2 instance types. Like we run into customers that are very, very heavily network oriented, but they don't consume any RAM. They just have, a few keys and they just want to hit them as hard as possible in their big data. So, you know, for those, like there's a C7GN instance, and if you use that versus an R7, you'll end up wasting all this extra RAM that's just sitting there because they have way more network. The C7GN has a quarter of the RAM, but a lot more network than an R7G. So being very, very thoughtful about what instance types. And then if you have the infrastructure as code, right, like, which I think we do, we made, we're not perfect, but we made a lot of investments. Different cells are running different instance types based on the characteristics of those cells. So we run our routing fleet as C7GN in some regions and as C7Gs in other regions, and it's totally fine.
Okay, and what are some of the specific optimizations that you've learned besides picking the right EC2 instance for each cell, but also for the for the I guess the query that the router layer as well?
Yeah, so we work a lot in terms of reducing the cost of the extra hop from the routing to the storage. And we spend a bunch of time, we rewrote our entire service in Rust. And one of the biggest lessons learned there was when we moved from Java to Rust, our ability to handle like the load was like neck to neck. We got like maybe a 5% increase. So, but over time, that's when you start getting into the hundreds of thousands of transactions per second on a single node, that's where techniques like core pinning and flow routing start to actually help you drive the box hotter and hotter. Other techniques, including placement groups, like AWS placement groups, are incredibly underutilized. Like it started as a high performance computing construct, but basically, if you want nodes to be very tightly grouped together and have low latency between each other, you can put them in a cluster placement group, and that meaningfully, it'll drop your latencies by to tens of micros between the two nodes, which sounds pretty inconsequential, but it really comes into play when you're trying to drive a lot of throughput between two nodes on a very small number of connections, right? Because there's the round trip delay actually um, increase reduces how many TPS you can do on a single connection. So placement groups, core pinning, and flow routing have been helpful once we moved on from the Java world into rewriting our entire stack with Rust.
Okay, I've heard about the core pinning, so that is mostly to do with trying to maximize your cache affinity, so that essentially the same user hits you again, you go to the same core, which you most likely have got some of the data in the L1 and L2 cache already. So that's the idea of core pinning. I've not heard about the flow routing before. What's that?
Yeah, so core pinning is more to make sure that so look, we have um, let's say you have a eight node 8 core Graviton instance. And what we would do is we would run 6 of those cores for our threads, and we would say, "Hey, thread, don't leave this." But the really important part is to then also say, "Hey, kernel, your networking is only happening on these 2 cores." Because when you start processing too many packets on the same node, the packet interrupt can actually disrupt whatever, like it can cause context switches in the cores that are doing useful work for you. So that's where real core pinning is not just core pinning your threads, but also the kernel and specifically the networking interrupts, the RQs to specific cores as well. Flow routing just means that hey, like you can say hey, this core is going to continue processing the request for that's coming for the same user. Like for this, and you can do that based on port and IP address as an instance for like the source, so that you're not switching, like you're not handing your stuff to a different thread for the same user over and over again as they send more data back and forth. And this becomes more important in different architectures where threads are just stealing work from each other and so forth. But flow routing is much harder. Like if you want to optimize, start by picking the right EC2 instance, check out placement groups, then core pin. Like you can do core pinning in a matter of like you can learn it from scratch and deploy it within the same day. But it's only useful if you're really driving your machine hot. Like if you're actually doing 100,000 plus transactions per second, core pinning goes a long way.
Right. I actually got the two mixed up. What I was thinking about as core pinning was actually flow routing. And core pinning is the stuff that
Yep,
I think the Erlang runtime used to do because they only run as many concurrent threads as there are cores in the CPU, precisely to minimize the percentage of CPU time gets spent on the context switching. Yeah,
exactly.
I think the Java, some of the Java frameworks used to do the same thing as well. That precisely for the same reason to try to minimize the amount of context switching. Okay, that's really cool. What about in terms of Rust itself? Is it because the techniques you talked about again? That's also applicable to Java and other languages as well. If, like you
Mhm.
said, you didn't get that much win out of just switching from Java to Rust. Was there anything specific about Rust? I know Evan talked about how Rust is high performance, all of that. But in your experience, what were some of the biggest wins from switching from Java to Rust?
You can write really slow code in Rust. That's just reality. And so don't expect that just by rewriting your application in Rust, like especially for the complex application, that suddenly everything is going to be much, much faster. Look, our team is filled with Java experts, and we have spent our entire lives like tuning JVMs to do whatever they could do. We learned Rust from scratch in the middle of this company, right? So there's a whole lot of techniques that we didn't know. And like there are issues in Rust libraries as well when it comes to like there are issues that we're actively debating with at the on the HTTP libraries inside of Rust where some of in certain scenarios it can actually be slower than Java. So at the end of the day, like you're not gonna get like there's no easy answer for performance. You still have to profile your application. You still have to find the sources of contention. You still have to deal with multi-threaded optimizations and so forth. So it's not an easy answer. You gotta keep tuning and going from a well-tuned Java environment to Rust, you may not get something great out of the box because you also may not know all the tricks, tips and tricks inside of Rust yet. It's been a worthwhile journey. It just took actual investment to improve.
Yeah, I wish more people talk about that. I think the way that a lot of people talk about Rust as if it's the silver bullet, the magic dust that you can just sprinkle on your application and suddenly it's 10x faster.
I mean, sure, like if you're just doing a hello world type of application, like yeah, it's pretty fast, but things get complicated when the application is more complex.
Yeah, absolutely, absolutely. Yeah, I think that's all the questions I've had. And anything else you want to sort of add before we go? Anything, I guess, any new things happening at the Momento? I know you guys were talking about Object a little while back. How's that coming along?
It's coming along really well. I We've been working on our favorite service S3 and adding a cache on top of it. We're finding all kinds of new use cases, especially in the AI landscape, about temporary data that needs to be really really fast when it's fresh, but needs to be persisted for long term. And S3 is incredible for low cost durability at very, very high throughputs. And then S3 plus Momento just pairs like the best, it's just a really nice pairing. So we've been excited about that. We love talking to customers that have deep performance optimization needs. And whether it has to do with Momento or not, we still want to talk to people because then we learn from them and then we allow our customers to get benefit from it. So if anybody wants to nerd out about deep distributed systems performance issues, I would love to get time and learn from you.
Yeah, and I guess in that case, if someone wants to reach out to you and talk to you, what's the best way to find you? Is it going to be on the X or Twitter or well, or LinkedIn or somewhere?
Yeah, I was about to say Twitter, but yeah, you can find me on Twitter, KSSHAMS, or LinkedIn. I think my DMs are open on both. Just shoot me a note. And then Momento is at gomomento.com. So just and you can also find me on the Believe in Serverless Discord. So believeinserverless.com, just join the Discord community. It's a really happening environment with over 1,000 members that are just helping each other grow, and that's where I learn a lot. And happy to meet more people there too.
Yeah, I'll put the links in the description below. And I have to say, the Believe in Serverless community is great. I really love jumping in there and occasionally just jumping onto a thread and they're talking about the problems people have because there are some really talented engineers on there, very experienced developers who are chipping in and helping each other out. It's great. It's a really good place to be if you want to learn about serverless, but also have fun talking about the more complicated, complex problems that the people may have.
Absolutely. And there's no zealots. Everybody's supportive. So even if you have questions about your Kubernetes cluster, bring them on over. We'll help you out.
All right. Okay. Yeah. Thanks for joining us again, and I'll see you hopefully in the next couple of months, maybe in Seattle. And
Yeah.
yeah, I'll talk to you guys next time. Take care.
Thanks, Sean.